And here's the crazy part. Some of these AI agents are processing more data in a single day than the entire Library of Alexandria held. We're talking about a fire hose of information, and if they can't remember what they've learned, they're basically fancy parrots.
A fire hose, huh? That's quite a visual. But seriously, what breaks when these AI agents can't hold on to their memories effectively? Isn't that just a chatbot that forgets your previous question?
It's so much bigger than that. Imagine a personalized recommendation system like Netflix without a robust memory. It's suggesting the same generic top 10 movies to everyone, ignoring your viewing history, your ratings, your preferences. No more, because you watched X, you might like Y. Just bland recommendations.
Okay, I see the business impact there. Lost revenue, frustrated users. So we're talking about moving beyond stateless interactions to something more persistent. How do we actually give these AI agents a brain that remembers things?
That's where embedding models and vector databases come in, the dynamic duo of AI memory. Think of embedding models as translators. They take messy, unstructured data, text, images, audio, and convert it into a structured numerical format called a vector embedding.
A vector embedding, so like a fingerprint for data, a unique numerical representation?
Exactly, a high-dimensional fingerprint. And the beauty is that similar data points will have similar vector embeddings. Now, the real magic happens when you store these embeddings in a vector database.
Okay, vector database. Is that just a regular database that's been vectorized? What makes it special?
It's more than just a regular database wearing a vector costume. A vector database is specifically designed to efficiently store and search these high-dimensional vectors. It uses specialized indexing techniques to find the nearest neighbors, the most similar embeddings, in lightning speed.
Nearest neighbors, so it can quickly find things that are semantically similar, even if they don't share the same keywords?
Precisely. Think about searching for restaurants near me on Google Maps. Under the hood, they're using vector embeddings to represent locations and user preferences. The vector database efficiently finds the restaurants with embeddings closest to your current location and preferred cuisine. It's not just about keyword matching, it's about understanding the meaning behind your query.
That makes sense. So embedding models create the memory, and vector databases allow us to retrieve it efficiently. Let's dig into the embedding models themselves. What are some popular choices, and how do they actually work?
Great question. One popular family of models is based on transformers like BERT, Roberta, and the OpenAI embeddings. These models are pre-trained on massive amounts of text data, learning to understand the relationships between words and phrases.
Pre-trained on massive data sets, so they already have a ton of world knowledge baked in?
Absolutely. It's like giving them a head start in learning. When you feed new text into these models, they use their pre-existing knowledge to generate a vector embedding that captures the semantic meaning of the text. The crazy part is that they can even understand context and nuance.
But how does the training process actually work? What makes them learn the relationships between words?
The training process is based on something called masked language modeling. The model is given a sentence with some words masked out, and it has to predict the missing words. By repeatedly doing this on massive amounts of data, the model learns to understand the relationships between words and phrases.
Okay, masked language modeling. Makes sense. So a company like Uber could use this to understand customer support requests, right? Embed the text to the request and then use a vector database to find similar, previously resolved issues.
Exactly. They could embed the text of the customer support request and then use a vector database to find similar, previously resolved issues. This allows them to quickly provide relevant solutions and improve customer satisfaction. They could even use it to route requests to the most appropriate support agent based on the semantic content of the request.
Okay, that's a solid example. What about the vector databases themselves? What are some popular options and what are the trade-offs?
There are several popular options, each with its own strengths and weaknesses. Pinecone is a fully managed vector database service known for its scalability and ease of use. Weaviate is an open-source vector database that offers a GraphQL API for querying data. And then there's Face, a library developed by Meta for efficient similarity search.
So managed versus self-hosted, essentially. What are the key considerations when choosing a vector database?
Scalability, cost, and ease of use are the big three. Pinecone is great for teams that want a hands-off solution and can afford the higher cost. Weaviate offers more flexibility and control, but requires more operational overhead. Face is a good option for smaller projects or for teams that want to build their own custom vector database solution.
Okay, so you've got your embeddings, you've got your database. How do you actually use this to build an AI agent that can remember things? I keep hearing about RAG, Retrieval Augmented Generation. Is that the key?
RAG is absolutely the key. It's the architectural pattern that ties everything together. In a RAG system, when the AI agent receives a query, it first uses an embedding model to convert the query into a vector embedding. Then it uses a vector database to retrieve the most relevant information from its memory.
So it's retrieving context from the vector database based on the query embedding.
Exactly. And here's where it gets interesting. The retrieved information is then combined with the original query and fed into a large language model, like GPT-4. The LLM uses this augmented information to generate a more informed and relevant response.
So the LLM isn't just relying on its own pre-trained knowledge, it's also leveraging the information retrieved from the vector database. That's how it remembers things.
Precisely. It's like giving the LLM access to a cheat sheet that's tailored to the specific query. This allows it to provide more accurate, relevant, and up-to-date responses. Think about a customer support chatbot that can answer questions about the latest product updates, even if those updates weren't included in the LLM's original training data.
Okay, that's powerful. So RAG allows you to inject external knowledge into the LLM's reasoning process. But wait, doesn't that mean the quality of the embeddings and the vector database search directly impacts the quality of the LLM's output? Garbage in, garbage out, right?
That's a critical point, Priya. The quality of your embeddings and the accuracy of your vector database search are absolutely crucial. If your embeddings are poorly generated or your vector database is not properly indexed, you'll retrieve irrelevant information, which can lead to inaccurate or misleading responses from the LLM.
So it's not just about throwing data into a vector database and hoping for the best. You need to think carefully about data cleaning, embedding model selection, and vector database indexing.
Exactly. And here's the counterintuitive insight. Sometimes less is more. It's better to have a smaller, carefully curated knowledge base with high-quality embeddings than a massive, poorly organized knowledge base with noisy embeddings.
Interesting. So focus on quality over quantity when building your AI agent's memory. I can see how that would be easy to overlook. What else do engineers typically get wrong when working with embedding models in vector databases?
One common mistake is neglecting to update the vector database when the underlying data changes. If you update your product catalog but don't update the corresponding embeddings in your vector database, your AI agent will be providing outdated information.
So you need a system for automatically updating the vector database whenever the underlying data changes, a pipeline, essentially.
Precisely. Another mistake is using a one-size-fits-all embedding model for all types of data. Different embedding models are better suited for different types of data. For example, a model trained on code might be better for embedding code snippets than a model trained on general text.
Okay, so choose the right tool for the job. Makes sense.
And finally, many engineers underestimate the importance of evaluating the performance of their RAG system. It's not enough to just build the system and assume it's working correctly. You need to rigorously evaluate its accuracy, relevance, and latency to ensure that it's meeting your requirements.
So A/B testing, metrics tracking, the whole 9 yards. What should a software engineer do differently after listening to this? What are the practical takeaways?
First, experiment with different embedding models. Don't just stick with the first one you find. Try out different models and see which one performs best for your specific use case. Think of it like trying on different pairs of glasses. Find the one that gives you the clearest vision.
Okay, experiment with embeddings.
Second, invest in data quality. Clean and curate your data before embedding it. Remember, garbage in, garbage out. Treat your data like you're preparing a gourmet meal. Start with the freshest, highest quality ingredients.
Data quality is key. And third?
And third, monitor and evaluate your RAG system continuously. Track key metrics like accuracy, relevance, and latency to think of it as regularly checking the engine of your car. Make sure everything is running smoothly and efficiently. If you don't monitor your memory, you'll forget to.
Solid, actionable advice. So, to build AI agents with long-term memories, we need embedding models to translate data, vector databases to store and retrieve it efficiently, and the RAG architecture to tie everything together.
Exactly. And remember, giving your AI agent a memory isn't just about storing data, it's about enabling it to learn, adapt, and provide more intelligent and personalized experiences. It's like giving your AI a brain transplant, a digital one.